All right, welcome back. So far, we've learned about the null and alternative hypothesis, as well as how to calculate the z-score. Today, we'll learn how to convert z-score into something called a probability value, which you all may have heard about, called the p-value. So let's get into it. So in the last session, we talked about the z-score, which represents the statistical distance of the sample mean from the hypothesized value of the population mean. In this session, we'll further that concept and see how we can convert the z-score or the z-stat to a probability score called the p-value. So you might have heard of this p-value or even seen it in scientific articles. A quick disclaimer, while it is one of the very popular statistics to report to indicate significance in a finding, it certainly is not the only one. And because of its popularity and mainstream use, in some cases, it could be misused and abused. So just be aware of that, and hopefully in the next couple of videos, we can make it clear to you what the p-value actually is. The p-value answers the questions: if the null hypothesis were true, then what is the probability of the observed test statistics, or one that is more extreme? What does that mean? Well, a small p-value will essentially tell you that the observed data is unlikely to have come from a distribution suggested by the null hypothesis. Even simpler terms, a small p-value will provide good evidence against the null hypothesis, or let you reject your null hypothesis. To make better sense of this, let's revisit our distribution, a very familiar distribution here, where the distribution of the sample mean as well as the z-stat that we calculated if the null hypothesis were true is represented here. So our hypothesized population mean is 170 and our z-stat calculated for that is 0. If you remember, the z-stat represents the statistical distance of a sample mean from a population mean. So that's why it's 0. There is no distance. It's also 0 mathematically, right? The z-stat equation shown here is the sample mean minus the hypothesized population value mean over the standard error of sample mean. So a 170 minus 170 is 0, and 0 over a value will result in 0. So that's why our z-score here is 0. Let's also look at a sample mean value of 173 and its z-score 0.6 as our first example. For z-stats, p-values corresponds to the area under the curve of the standard normal distribution. So to convert our z-stat to p-value, we can consult what's called a standard normal table, which looks like this. This was generated by using the normal distribution function in Excel. Essentially, we look at our z-score, which is for 173 is 0.6, right? And we're gonna go down all the way here to find 0.6, which is here. It's negative 0.6, and that's because we're looking at the area to the right of our z-stat or our z-score. And also it's gonna be the 0.00 here, since there's no value after the 0.6. So we go down that, and we come to a p-value of 0.2743. So let's go ahead and write that down. So this p-value of 0.2743 under the area of the curve, and we shade it in, that looks like this. This essentially indicates that a result of this extreme will occur 27.4% of the time when the null hypothesis is true. Since this isn't very surprising, the evidence against the null hypothesis here is weak. Now let's look at an example where the sample mean value is 185. From our normal distribution table, we get a p-value of 0.013, which is a very small p-value, right? And it says that a result this extreme will only occur 1.3% of the time. But when it does occur, it will provide us strong evidence against the null hypothesis. Great. One last thing to be aware is that p-values rest on the assumption that the null hypothesis is true. Therefore, it is the probability of the data given the null hypothesis and not the probability that the null hypothesis is true given the data. Thank you.